Section 4.6 Rank. First we're going to look at the row space. The set of all linear combinations of the row vectors of a matrix A is called the row space of A and is denoted by ROW or row A. And we know that when we're talking about dimensions of a matrix, we have m by n matrix. So our matrix A might be m by n, which means that there are n entries in each row. So then the row space of A is going to be a subspace of Rn. So let's look at an example. We've got a matrix A given here, and we've got these vectors, and these vectors R1, R2, and R3, these are horizontal row vectors. So when we're talking about the row of space of A, it is equal to then, remember, the set of all linear combinations of the row vectors of our matrix A. And that is equal to then the span of our three row vectors, R1, R2, and R3. And in this case, this is a subspace of R4, since our vectors are in R4 space. We can express row vectors either horizontally, as we just did in that previous example, or as column vectors if you prefer. So given that, we know then that the column space of A transpose is equal to the row space of A. Now let's look at Theorem 13. If two matrices A and B are row equivalent, and that's important, we're saying they're row equivalent, then their row spaces are the same. If B is in echelon form, the non-zero rows of B form a basis for the row space of A as well as B. So then what we're saying is that the row space of A is equal to the row space of B. And this is assuming our two matrices are row equivalent. Let's look at another example. We have two matrices A and B, and we're told that they are row equivalent. So we want to find a basis for the row space, the column space, and the null space of A. And then also we want to state the dimension of each. So remember that the dimension is just the number of vectors in our basis. So once we find the basis, then the dimension is easy to come by. So by Theorem 13, we know that the first two rows of B, remember 13 says that the non-zero rows of B form a basis for the row space of A as well as B. So the first two rows are non-zero rows, and they form a basis then for the row space of A, which is equivalent to the row space of B. So then we can say that a basis for the row space of A is equal to these two vectors here, which you'll notice are the two non-zero rows of B, okay, and they are not the rows of A. So when we're talking about the row space of A and we're using Theorem 13 and we're using this echelon form, then it's the rows of B that form a basis for the row space of A. And so now we can give the dimension of the row space of A, and since there were two vectors in our basis, we know that the dimension is 2. For the column space of A, we need to recall what we've done in previous sections. Remember, when you're trying to find a basis for the column space of A, then we look at our echelon form here of B, and so let's kind of erase what we had from the row space. We're looking then at where our pivots occur, which is in the first two columns. So those two columns of A over here are going to form the basis for the column space of A. So then our basis for the column space of A is equivalent to these two vectors, which were the first two columns of A. So now the dimension of the column space of A is going to be 2, since there were two vectors in our basis. So now we want to look at the null space, and we want to find a basis for the null space. So remember that we want to take our matrix A and set it up in an augmented matrix with a column of zeros, and we want to row reduce it. So when we do that and we row reduce it, we will get this matrix here. So I want to find the general solution, and I have that x1 is equal to 3x3 plus 6x4. x2 is equal to 0, and then x3 is free and x4 is free. So I have x3 then times 3, 0, 1, 0 plus x4 times 6, 0, 0, 1. And so then these two vectors in our general solution are going to be in the basis for the null space of A. So I've simply written the basis for the null space as a set containing those two vectors. And since our basis set had two vectors in it, we know the dimension of the null space is 2. Now notice that for these first two, the row space and the column space, we could use any echelon form, which is why we were able to use B over here. And we didn't have to have one with zeros underneath and zeros above. However, for the null space, it's important that we use the reduced echelon form in order to find the general solution. Let's look at the following. The dimension of the column space of A is simply the number of pivots of A. And that is equal to the number of non-zero rows in B, which is the dimension of the row space of A. Also, the dimension of the null space of A is equal to the number of free variables, which is equal to the number of non-pivot columns of A. So that leads us to a definition. The rank of A is the dimension of the column space of A. So we have this holding up here, this relationship. The rank of A equals the dimension of the column space of A, which is the number of pivot columns in A, which is equal to the dimension of the row space of A. So we can set it up here then. The rank of A, which is the number of pivot columns, as we said kind of up here, of A, plus the dimension of the null space, which is the number of non-pivot columns of A, should add up to equal the total number of columns in A, which was n. So now we're ready to introduce Theorem 14, the rank theorem. The dimensions of the column space and the row space of an m by n matrix A are equal. This common dimension, the rank of A, also equals the number of pivot positions in A and satisfies this equation that we just looked up in the previous slide. The rank of A plus the dimension of the null space of A is equal to n. Now, since we know that the column space of A transpose is equal to the row space of A, we looked at that a few examples earlier, then we can say that the rank of A is equal to then the rank of A transpose. In this example, we're going to suppose that a 5 by 8 matrix A has a rank of 5. So we want to find the dimension of the null space of A, the dimension of the row space of A, and the rank of A transpose. And then we want to answer the question, is the column space of A equal to R5? So we have our formula here. The rank of A plus the dimension of the null space of A equals n. We know that the rank is 5. We know that n is 8. So we need to find then the dimension of the null space. So solving that simple equation here, we know the dimension of the null space is 3. Also, the rank of A is equal to the dimension of the row space of A, which is equal to 5, since that was the rank. And then also, since we know that the row space of A is equal to the column space of A transpose, then we know that the dimension of the row space of A is equal to the dimension of the column space of A transpose. But then that is equal to the rank of A transpose, which is equal to the rank of A, as we just saw above. So we can then say that the rank of A transpose is equal to the rank of A, which is 5. So we found those three parts, and now we need to answer our question: is the column space of A equal to R5? Since the rank of A, which is the number of pivots in A, is equal to 5, then that means there's a pivot in every row. Since it's a 5 by 8 matrix, then we have 5 pivots. There's one in each row. So then we know that the columns of A span R5, and this is by that important theorem 4 from our first chapter that we looked at, those with the 4 pieces that were equivalent. Since we have a pivot in every row, we know that the columns of A span R5. Hence then the column space of A is equal to R5. So the answer here then would be yes. In this example, we have a 9 by 12 matrix A, and we want to find the smallest possible value of the dimension of the null space of A. So we have our formula: the rank of A plus the dimension of the null space of A equals n. And so we have our m by n matrix here. So then we know that n is 12. So if I solve this, then I know the dimension of the null space of A is equal to 12 minus the rank of A. So I've just replaced n with 12 and subtracted the rank. So in order to find the smallest possible value of our dimension of the null space, then I need to look at subtracting the largest possible value for my rank of A, which is the number of pivots. So the largest possible value for the rank of A is the largest number of pivots that I can have. Well, if I have a pivot in every row, I only have 9 rows, so I know then that the largest possible value I could have for the rank is 9. So then we know that the smallest possible value of the dimension of the null space of A is then equal to 3, since 12 minus 9 is 3. So it could be bigger than that, but that's the smallest possible value. Can't be smaller than that. In this example, we're given a matrix A, so one can easily verify the following. First, we want to find a basis for the null space of A. And so to do that, we're going to row reduce our matrix A. And so when I row reduce it, I will end up with this matrix here. And so then the general solution, I have that x1 is equal to x3, x2 is free, and x3 is free. So then I would pull out x2 times 0, 1, 0 plus x3 times 1, 0, 1. So those two vectors are in the basis for my null space of A. So since we have two vectors in my null space of A and they are in R3, we know that the null space of A is a plane in R3 space. Now we want to find a basis for the row space of A. So remember that when we reduce it to an echelon form, then my non-zero row is the basis for the row space of A. So we could say that it is this column vector 1, 0, negative 1 here, or we could have written it as a row vector 1, 0, negative 1. So then the row space of A is a line in R3 space. Now we want to look at a basis for the column space of A. So remember that we row reduced our matrix A and we got this matrix up here. You could call this your matrix B. So my pivot was here in the first column. So that means that the first column of A is in the basis for my column space. So it's simply got this one vector here. So then the column space of A is a line in R2 space. And now let's look at a basis for the null space of A transpose. So we'll kind of come down here and write down A transpose, which is going to be 1, 0, negative 1, 2, 0, negative 2. When we row reduce it, we get this matrix here, and we'll go ahead, since we're dealing with the null space, and add our column of zeros. So we have that x1 is equal to negative 2x2, and x2 is free. So we'll pull out x2 times negative 2, 1. So then the basis for the null space is simply going to have that vector in it, negative 2, 1. So then the null space of A transpose is a line in R2 space. So let's look at a graph. In this one we're looking at the subspaces null A and row A. So here, remember, the null space of A, and this is from our example before, was a plane in R3 space. And then the row space of A is here, and it was a line in R3 space. So we're dealing with 3 dimensions. Now we're looking at the subspaces null space of A transpose and the column space of A. So if we look, we have the vector 1, 2 is right here. And then our vector negative 2, 1 is right here. So the vector containing 1, 2, this was the column space of A, which is our line in R2 space, and then this one containing negative 2, 1 was the null space of A transpose, which was another line in R2 space. The rank theorem then provides us with a powerful tool for determining information about a system of equations. So in this example, a scientist solves a homogeneous system of 50 equations in 54 variables and finds that exactly 4 of the unknowns are free variables. Can the scientist be certain that any associated non-homogeneous system with the same coefficients has a solution? So first we want to recall that the rank of A is equal to the dimension of the column space of A, which is equal to the number of pivot columns of A. Also, we need to recall that the dimension of the null space of A is equal to the number of free variables. So in this case, we have a system of homogeneous equations, so AX equals 0, where A is a 50 by 54 matrix. So this was our M by N. We had 50 equations, so that is the number of rows, and 54 variables, so that's the number of columns. So by the rank theorem we have our formula. The rank of A plus the dimension of the null space of A is equal to N. And remember that the dimension of the null space we set up here is the number of free variables. So the number of free variables we were told here is 4. So we have 4 here, and N is 54. So the rank of A then plus 4 is equal to 54. So then I know in solving that equation that the rank of A is equal to 50. And the rank of A is equal to the number of pivot columns of A. So if I have any non-homogeneous system, since I know that there are going to be 50 pivots and I have 50 equations, then there will be a pivot in every row. So any non-homogeneous system, AX equal B, has a solution because there is a pivot in every row. And so now we can add some more to the invertible matrix theorem. We're going to let A be a square n by n matrix, and then the following statements are equivalent to the statement that A is an invertible matrix. We have M, the columns of A, form a basis for Rn. In N, the column space of A is equal to Rn. O, the dimension of the column space of A is equal to n. P, the rank of A is equal to n. Q, the null space of A is equal to the 0 vector. And R, so then the dimension of the null space of A is equal to 0. And remember, if our matrix is invertible and I have a pivot in every row, then I don't have any free variables. So that's why the null space of A is the 0 vector and the dimension is 0.